Well, we have just been studying how if we increase the temperature, in other words, we add heat to something to raise its temperature, how for a solid it will change its length, and how for a volume of a solid, liquid, or gas, it'll change the volume. And that's almost always an increase. We'll learn later what that exception is. But it's an exception because we can anticipate that when we heat something, it's going to expand, whether it's by volume or by length. But now we're going to look in this section, 16.3, at how we can add heat and raise the temperature also. Heat raises the temperatures of almost all substances except during a phase change. Now, a phase change is when you go from a solid to a liquid to a gas, or a gas to a plasma. Those are called phase changes. During a phase change, we have a different type of equation, and the temperature does not increase. The heat that is added serves to change the phase, but not increase the temperature. But if we're not changing the phase, the temperature will rise. And this is how much? This is the critical equation that we have. When we have an amount of heat, I really should have put a delta Q here. If I put a delta Q of heat into something that has a mass M, then it will change the temperature by delta T. And this C here is called the specific heat. The specific heat of the substance. Whether it's water or copper or wood or glass or whatever that substance might be, we will get a different specific heat that is a different change in the temperature for a given amount of heat that's been added. If we think back about our definitions, you can imagine that we actually defined the specific heat of water to where we had 1 kilogram. If we change it 1 degree, this would be 1 calorie. However, we're now going to use joules, and if we use our energy in joules over here, and we use kilograms here and degrees Celsius here, water turns out to have a C for water, which is equal to 4186, which is, in fact, the number of joules that is in 1 capital calorie, that is a kilocalorie, the calorie we eat. So when we eat a calorie, it's 4186 joules that we're eating. Mercury is just 139, very different. Aluminum is 900. Glass is 840, and lead's 128. Well, gosh, I think you can see from this that water, in fact, requires a tremendous amount of heat to change the temperature by a small amount. Now, this is for anything when we're heating something. So let me draw a diagram here before we get into the phase change, and let's just imagine water for a while. If we take something like ice, and we take ice, and remember, ice can be at all different temperatures, and this is the heat, this is the temperature, and this is the heat that we're going to add. So we keep adding heat and the temperature goes up. Then suddenly it gets to the point where it begins to melt. And as it melts, it goes through a phase change and the temperature does not change. This is going to be 0 degrees Celsius. And we keep adding heat and keep adding heat, and we say, well, what happens to it? Why is it not getting hotter? The answer is because that extra energy is going into melting the ice. Finally, when it's all melted, it then begins to go up a new slope, a different slope from this one. This is now water. So now we have all water. We get up to a new temperature, and at this new temperature, suddenly it goes flat again, and this is when the water goes into steam, and at a certain point, it begins to boils away. So it's boiling here. It's either melting here or freezing this way. So you melt this way, freeze this way. You boil this way, you condense this way. You're going from water to steam, and you're on a different curve. And so ice, water, and steam all have a different slope. And the the specific heat is different for those different substances. And these are considered different substances here. And so you have to look up what the specific heat is of ice and so forth. So now we know how to relate this slope. That's what this curve describes, is here, here, and here. This is this important equation here that tells us what the specific heat is as the constant proportionality between, for a given mass and the temperature change, how much heat is required to give that temperature change. The next thing we're going to look at is what is called a phase change. And these are the phase changes here. And the phase change does not involve the temperature. And you'll notice that the equation there is Q. It's just mass times L. In other words, the amount of heat that you need to change the phase for a given mass is a constant. And that constant is called the latent heat. What kind of latent heat? This is latent heat. This latent heat L is like the C is up here. The C is the specific heat. This is the latent heat. Latent heat is used for phase changes. And there's no temperature involved here. And this is the heat necessary to take this mass and for ice and water to convert it between the two, or to convert it again from water to steam, and so forth. And if we look at the latent heat, we're going to have two different kinds for each substance. One is the latent heat of fusion. A fusion is this transition right here, when we go from solid to liquid or liquid to solid. We're performing a fusion. If we think of the liquid going back to a solid. Then there's latent heat of vaporization. That's sometimes called freezing. It's melting or freezing. And then we have the latent heat of vaporization. When the substance changes from a liquid to a gas. When we take the water and we boil it and make steam, we have the latent heat of vaporization. And to give you some examples of these latent heats, water, now this is, first I'm going to give you the latent heat of fusion, then vaporization. Water is 33 e to the fourth, and then 22.6 e to the fifth. Gold, there's the two numbers, nitrogen, and so forth, and we can see what the different substances are. But in particular, let's choose water. Let's imagine you have 4 kilograms of water. And you want to take those, and you want to take them from a frozen state of ice at 0 degrees Celsius, and you want to take it to water at 0 degrees Celsius. Same temperature, but you want to melt it. So first it was ice, now it's going to be water. That would require an amount of heat Q, which is equal to the mass, 4 kilograms, times the latent heat of fusion. The latent heat of fusion for water is 33.5 e to the fourth. And so it would require 4 times as much. 4 and 5 is 20, 3 and 4 is 12, 14, 3 and 4 is 12, it's 13. We have 1 decimal place, so it's 134 e to the fourth. So it's going to be 1.34 times e to the 456. And that would be how much heat we'd need in order to take that 4 kilograms of water and convert it from ice into liquid water. You can do the similar kind of calculation here. We're taking water up a given distance. We could say how much would it take to take that same 4 kilograms and heat it to boiling. The answer is you would put the 4 kilograms here. So the amount of heat necessary to do that would be C, which is 4186 joules, times the 4 kilograms, times 100 degrees, because you're going to take it from 0 degrees up to boiling. or to some other temperature point, and you'd simply multiply these three numbers to say how much heat is needed to move you up this curve. So on the test, you can expect to be able to go from one point to another point on the sloping curve, that is using specific heat, and on the flat part of the curve where we're changing phases, and there we use the latent heat of either fusion or vaporization.